So hello everyone, welcome to D block elements, and in this lecture we will be covering D block elements, and this is the first lecture of D block elements, and in this lecture we will be covering the properties, trends and oxidation states of D block elements. And basically I have covered the entire NCRT here for JEE main only, so let's begin. So this is the D block, this is the period table, and basically we have done the D block. We will do F block next time. S block is not in your syllabus, although we have learned flame tests for these and SWOT analysis, and the rest elements is here which are the green in color. They are called the D block, and they are basically called transition metals as well. Why are they called transition metals? Because they are in transition between the S and P blocks, so they are called the transition metals. Well, except for these guys, but we'll learn about them later. Now, what do these stars mean? These stars mean that they show exceptional electronic configuration. We will see, and the first series is called 3D series, second is 4D, 5D, 6D, and we call it ND because basically this is n minus 1D, where n is the principal quantum number. Here you can see this is the fourth period, but still this is 3D, and this is thanks to the Aufbau order. And so let's begin with the introduction. We call D block elements transition elements because they are transition between S and P block. And what is the formal definition of a transition metal? It is basically a metal which has incomplete d subshell in its base atom or its common oxidation state. For example, if you look at palladium, palladium has a full d10 electron configuration, but we say that incomplete ones are called transition metals. But still, if we oxidize palladium, it is going to lose electrons. It will become d9, d8. I don't know the state of palladium, but still, it will lose an electron, and then it will have an incomplete d subshell. And that is still why we call palladium a transition metal, and same for all the others, which may seem like exceptions but aren't. Now, zinc, cadmium, and mercury, like zinc, cadmium, and mercury, and even copernicium, they are not transition metals because even in their common oxidation states, they still have a full D10 configuration. Like Zn has configuration for S2 3D10, but Zn2 plus has configuration 3D10. And zinc does not show any other oxidation states. So zinc is not a transition metals because of the full subshell. But there are just three elements. Why should we make a separate chapter for them? So we studied them along transition metals. Okay, that was the introduction. Now let's learn about the electronic configuration. A very generalized version of the electronic configuration is whatever into n minus 1d, this can go 1 to 10, and n is 1 to 2. And most likely 2, because the ones where ns is 1, they are considered exceptional electronic configurations. Like here, the ones which I have marked in red star, they are the ones in which the s subshell has 1 electron instead of the expected 2. And palladium is special because this is the only one I know which has 0 electrons in the s subshell, and instead it has a fully filled d subshell. So yeah, these are the exceptions. The most notable ones you should know are, you should know along with the configurations is copper, chromium, and palladium. Copper was expected to be 3d9 and 4s2. Chromium was expected to be 3d4 and 4s2. But as you know, this transition occurs because fully filled and half filled subshell comes, and again this grade of stability is enough to convince palladium to donate both of its s electrons into a d subshell to get a fully filled d orbital. And niobium, molybdenum, ruthenium, rhodium, silver, platinum, and aurum, or which we call gold, they also have 1 electron in their s subshells. And JMA 2025 asked a direct question on this, where you had to tell the total number of d subshell electrons of niobium and I guess ruthenium when added together. So a very general method for that is you write the basic electronic configuration and just move one of, like, you write it normally following the Aufbau order without any exceptions, and then you know that these are exceptions. So you must have written ns2 n minus 1d whatever. So just take one of these from here, make it 1, and add plus 1 here. Okay, but for this you need to know their atomic numbers, so let's take a look at that. Well, if not even the fifth series, you must remember that third series is very, very important, like 2 stars. And fourth series they also ask questions, so this is 1 star, although not as important as the third series. And basically in the third series there's only chromium and copper. It's easy to remember because this is close to a half filled one, this is close to a full filled one. In the 4D series, you have to remember that technetium, to the left side there are 2 exceptions, and to the right side there are 4 exceptions. Okay, you have to remember this, or maybe you could remember that cadmium is not a transition metal, so technetium, zirconium, and yttrium are the only ones which follow the Aufbau order in the fourth one. Okay, so that was it about the general electronic configurations. Let's talk about some general points. Now, d electrons have very poor screening effect. We learned that s subshell is better at screening than p, d, and then f. Why is that? It is because the s subshell spends more time closer to the nucleus, while the d subshell it is like scattered. Okay, so it is very poor at screening. Like you can see, this has no protection here, and it spends its time away from the nucleus, so it protrudes to the periphery. Like basically, it spends more time near the boundary of the atom, and it protrudes to the periphery more than p or s electrons, and hence, as a consequence, it is more influenced by its surroundings. Now, these are some general properties that d block elements show, that they have catalytic property, paramagnetism, multiple oxidation states, colored compounds, and complex formation. All of these we will cover in the next lecture, except for multiple oxidation states, which we will cover in this lecture. Okay, so we will do that just so. Now, in S block, we know that even if S block is related, a general point that this group is similar. This group is similar. In P block also, this we studied together. But in D block elements, instead of top to bottom, there is similarity between the elements from left to right. Okay, and later on, in heavier elements, top to bottom similarity also comes, but it's rare. We will learn about it. So, even more important than P block are the physical properties of D block elements, and this is going to give you a tough time, but I will try to make it as easy as possible. So, very generally, they have metal-like properties because non-metals only exist in the P block region. So all of the D block elements, they are metals. They are malleable. Means it is easy to take one of these and just flatten it into a sheet of paper, something like the Rutherford experiment. It used the gold sheet, which was like 1,000 atoms thick, like that is incredibly thin. Okay, so that just illustrates the malleability of a D block element, and they're very ductile as well. Like if you look at copper, we use it for wiring, so that is very ductile. Ductile is basically, it can be made into long thin strips, which is called wire. They have high electrical conductivity, also high thermal conductivity as well, and they have metallic luster, like they shine. So let's learn about the lattice structure, and luckily they follow a very simple trend. You just have to write all of them in a straight line, and the first pair will be an HCP or a BCC, second will be a BCC, third will be HCP, and the last trio, except the non-transition ones, they will be CCP. Now, what is HCP, BCC, HCP, CCP? Basically, it's nothing but it is a measurement of how the metal atoms are aligned together in a lattice. This is a very terrible diagram, but since I also haven't studied solid state yet, I don't know what these structures actually look like. But if they are mentioned in NCERT, those are important. Solid state is removed from the syllabus, by the way. Just remember the full forms. BCC is body-centered cubic, HCP is hexagonal close packed, CCP is cubic close packed, and for the non-transition one, they are just typical metal structures. Okay. So that was it about lattice structure and their basic properties. Now, keep in mind melting points. They are the most important ones, most important physical properties. So, all the transition elements, they are hard metals. Of course, with the exception of zinc, cadmium, and mercury, they have D10 configuration and they are called soft metal. Okay. Now, they have high melting point and boiling point due to the d electrons taking part in metallic bonds. Like basically, they form metallic bonds with each other, and this gives rise to a very strong lattice. And if you don't believe me that they have high melting point and boiling point, try boiling iron. You won't get iron liquid using conventional methods at least. So they have high melting point and boiling point due to the d electrons taking part in metallic bonds. And this is a very interesting point, that the melting point and boiling point, they are directly proportional to the number of unpaired electrons. We will find out how to find the number of unpaired electrons, but just know that as a general manner, like if this is the d subshell, and say it has a configuration which mentions the word D8. So using Pauli's principle, you draw one electron in each subshell, each degenerate orbital, before starting the pairing of others. So this is D8, and there are two unpaired electrons. So these unpaired electrons, they give rise to better metallic bonding. Okay. Hence the melting point and boiling point are directly proportional to the number of unpaired electrons. Now, there is an interesting thing here. Like, if you look at the periodic table again, in the fourth guy here, like from here to here, the fourth guy has the highest melting point. Why so? Even though we know that the middle ones, they are the most stable because of D5 configuration, half-filled configuration. Why are they having the highest melting point? Let's learn that. Well, this is because that, say this is manganese. When you put this is a half configuration, half filled D subshell, and this gets exceptionally stable. And if you want to make bonds with anything, you will have to let go of this stability to form any bond in the first place, which it does not want to do. Okay, which is why the manganese melting point, it falls below that of chromiums, and similarly the melting point of technetium falls behind that of molybdenum and ruthenium. And here you can see it's a constant decrease after tungsten, but still it is observable that the melting point of rhenium drops below that of tungsten. Okay, that's was it. But for D5 it is low because electrons don't want to bond. After D6 is crossed, like after rhenium, this is D5. So after D6, osmium, ruthenium, iron, after those are crossed, they start pairing up. Like as I showed you, after the 5 degenerate orbitals are filled with one spin electron, the opposite spin electron starts piling up after the D6 configuration starts filling. So as we move on, the number of unpaired electrons decreases and hence the melting point falls as illustrated. So that was it about the melting points. Let's now learn about the enthalpy of atomization. Let's learn the formal definition first. The enthalpy of atomization is the heat released or required when 1 mole of a substance is broken into its gaseous atoms at standard temperatures and pressure. And this helps decide the E0 cell, basically spontaneity of any like change in oxidation state. And we will see how it helps decide that, but this is the main definition. It is the energy required when one substance is broken into gaseous atoms at STP. So, as you can see, this curve is very similar to that of the melting point. Like this bird-like shape, we see both places. So most of its properties are similar to that of the melting points. And basically, what does it all relate to in there? It relates to the strength of these metallic bonds. If this metallic bond is strong inside the lattice, the melting point will be larger, and the enthalpy of atomization will also be large because it's hard to take them apart from each other. Oh, I draw hyperbola. But if say this bond is very weak, they don't like each other. So it's easy to separate them by providing energy, whether it be via the enthalpy of atomization or whether it be via melting. Okay. So as I said, similar curve to melting point. And metals with high enthalpy of atomization tend to be inert in chemical reactions. Like not as inert as in noble gases, but rather inert. And this is a very obvious point. Like if something has high enthalpy of atomization, it's hard to convince it to go into the gaseous phase to basically just react. Okay. And enthalpy of atomization has a necessary condition that you have to go into the gaseous phase. Now, while they haven't asked a direct question from the order of elements of enthalpy of atomization, I have created a memory aid to help you remember this order, and we'll come to it later, but one second I want to tell you that the 4D series and the 5D series have higher enthalpy of atomization than the 3D series because they have more frequent metal bonding. Okay. Now let's learn the mnemonic. Basically, the order is vanadium has the highest enthalpy of atomization, and zinc has the smallest enthalpy of atomization. And the order is vanadium, titanium, nickel, cobalt, iron, chromium, copper, scandium, zinc. Wait a second, I forgot to add manganese. Well, just remember that this guy is out of the transition elements and manganese is basically the last. So while this is not in the mnemonic and I don't want to think of a way to add it, just know that zinc has D10 configuration, manganese has D5 configuration. Hence they are from the same family. Not the same family, but they are the same, you know in what way they are the same. They have extra stability and hence higher enthalpy of atomization. So the mnemonic is you have gotten a new college. You live in Kerala. You live in Kerala. I don't know how to draw Kerala. This is Kerala. And you get a new college in Kumau. Kumau is basically a hilly area. Okay, so you are going there via a van, and basically this is a complex where a lot of college and school is there, but we call it the school zone. Okay, so van to new college, van to new college from Kerala to Kumau school zone. Okay, and remember manganese is here, like before zinc but after scandium. So this is our memory aid for the enthalpy of atomization. This isn't as important as the atomic radii, but still remember it. Now we come to the size. Okay, size decreases left to right like normal, but in D block this trend only goes on till the center of the period because Z effective till that point is overpowering the electronic repulsion. Like basically if this is the atom, the effective nuclear charge is like every increase in atomic number, one electron is being added, like I added another. So these electrons are repelling each other, but the added positive charge here, it counterbalances it and it makes up for it, compensates for it basically. But after the middle point, the inter-electronic repulsion, it gets so strong, they hate each other that much that they're willing to stray away from their nucleus, and the effective nuclear charge cannot keep up with their hate, so they are very like less bound, you can say, and hence the radius increases and electronic repulsions overpowers Z effective. Although the increase is gradual, it is still a formidable increase, and we should know it as a fact that after the middle element, the radius starts increasing. Now, if we talk about individual series, the 4D and 5D series have similar radii as you can see, and this is because of a phenomena called the lanthanide contraction, which we will do in more detail in the F block elements, but I can tell you a basic idea. Between the 4D and 5D series, there is basically a 4F subshell, and this 4F subshell is terrible at shielding. So basically the effective nuclear charge is too strong, and the F subshells, they cannot take care of the outermost electrons, they cannot shield it, so it just pulls and the radius drops. In fact, a 4D element, which is zirconium, is greater in size than a 5D element, which is hafnium. And in the third subshell, the memory aid for the order of metallic radii, they asked a direct question in JE 2024 and also in 2025. So you know how in J or NEET examinations, the reserved categories have lower cutoffs. Okay, so don't take any offense to this. This is just a memory yet that, and this is in Hindi. So the order is basically scandium, titanium, manganese equal to zinc. You know, they are brothers. One is D5, one is D10. Both are stable. Then followed by vanadium, chromium, copper, iron, cobalt, and nickel. So the mnemonic is basically you are a dude who has this reservation and you have cleared the cutoff and now you're going in new college. Okay. So what's the mnemonic? ऐसे तो मैं ज़रूर हूँ भाई clear cutoff फिर college new. For the non-Hindi speakers, this translates to I am an SC reserved student and I have cleared the cutoff. I will go into a new college. Okay. So you have to use this to remember the size of the D block elements in the third one. You don't need to remember the fourth period. So that's it. Let's move on then. Oh, and keep in mind one thing. In the earlier mnemonic, we used new college. Like nickel came before cobalt. But in size, cobalt got bigger than nickel. Now how do I remember this? Well, you have to keep in your mind that enthalpy of atomization and the size, they have conflicting cases where one nickel is greater than cobalt and one where cobalt is greater than nickel. So just remember that we learned a trend here that towards the end of the period, the electronic repulsions overpower the Z effective and the radius increases. So if you know remember the 3D series, you will know this is obvious that nickel is going to beat. So what can we do to, sorry I had to cut off recording in between. So what can we do to remember the that in size it is actually we are doing cobalt greater than nickel. So you know college you are going, so it is a big campus, so it has big size. So just remember that in size cobalt is greater, and you know in your mind that these are conflicting cases where the size and enthalpy of atomization have different orders for cobalt and nickel. So your mind will automatically remember that here nickel has taken the lead. Okay, and that's it. Now let's talk about the density. As the atomic volume decreases as we go left to right, we know the radius. So volume is proportional to the cube of the radius. So of course, if radius has a regular trend, volume also has a regular trend. And but the atomic mass increases thanks to the increase in neutrons and electrons being added to the shells and also protons. So volume is increasing, mass is increasing, density is mass upon volume. Numerator increasing, denominator decreasing. Density will blast, like it will increase skyrocketedly. Okay, if that's a word. And also density increases left to right very evidently, but zinc is an exception because it has large atomic volume. Basically, density of zinc it falls below that of copper, sorry, that of cobalt, nickel. Okay, and these are extra points the NCRT mentioned that enthalpy of atomization is maximum for vanadium, and it is least for zinc in the 3D series. First and third ionization enthalpies are maximum for zinc, and the second one is maximum for copper. This is quite understandable, honestly. And all of these they are minimum for SC. Again, useful you can use that cutoff fact. SC has the lowest cutoff. So ionization enthalpy, in order to take out this electron, you need to provide the least energy because this energy has a reservation. Okay, this electron has a reservation, and density is maximum for nickel and copper, and it is minimum for SC. You know how to remember that. Now let's learn about the ionization enthalpy. Ionization enthalpy follows an irregular trend. That means there is nothing you can do to predict. There's no left to right, there's no top to bottom. So why does it have an irregular trend? Well, it's because there's electron repulsion, there's shielding, there's different oxidation states being stable than the others. And the main point is that if you remove an electron, it alters the energy of the two subshells in question, and they can always go on top of each other or bottom of each other. Maybe they can be degenerate also. So this irregular trend is followed. But this hasn't stopped our dear agency from asking any questions from ionization enthalpy. So I have attached a sample question here. And in order to solve such questions, you have to remember two general points that the firstly the s electrons are lost before the d electrons. Like say if I have scandium, okay, if I have scandium and if I ionize it, the electron will go from s first. If I ionize it again, it will go from s again. Now s is over, so the last ionization will cause the electron from d to come to me. Okay, so this is the first thing. And also half filled can cause exceptions. Like you have to remember that if an atom is already in a half filled state, it will not want to leave that state. And if an element is getting access to the half filled state, it will be very spontaneous and will be willing to do so. Now this has two special exceptions which we will learn later, but this is generally true. Okay, and what factors control the ionization energy? nucleus electron attraction, electron repulsion, and exchange energy. Exchange energy is a fancy way of saying half filled. When a lot of electrons of the same spin are there, they can sometimes exchange positions, which causes them to release energy, and it imparts extra stability to the system. Okay, now let's look at this question, and it has been given to us that out of scandium, titanium, vanadium, chromium, manganese, and iron, we are considering the ion with the highest second ionization enthalpy. So if we ionize this in our mind, we know scandium is going to have a D0 configuration. No, it will still have a D1 configuration because the s electrons will go. Titanium will have a D whatever configuration, but it will not be 0 or anything close to 5. Like this is what should go through your mind. Of course, I can do it formally, like write down the configurations, but in the exam I don't have time. So I'm thinking from your point of view. Vanadium lies below chromium, manganese, like lies before that. So vanadium is not going to have any correlations with the half-filled state, and especially if I'm ionizing it, because that is going to remove electrons and not give it any chances of going towards a half-filled state. But chromium, however, I learned that this is an exception. Chromium has an exception of 4s1, 3d5. Okay, and basically if one ionization is done, I will be left with a half-filled substrate. And if I try to ionize it again, chromium is going to jump out of the screen and slap me in the face because it is already very stable. And if I try to ionize it, it's going to not be happy about it. So chromium has the highest second ionization enthalpy. So we are asked the spin only magnetic moment value of M plus ion. So that of the Cr plus ion. Cr plus ion has, as we talked about just now, it has the 5 configuration. And that means it has 5 unpaired electrons, and just use root n into n plus 2 to get 6 as an answer. So that was it for ionization enthalpy. Now we are going to learn about oxidation states. What oxidation states can we expect from the D block elements? This is a screenshot from the NCERT, and we can see that the ones which are circled in purple are the most common oxidation states for the highlighted element. Now, if we say that in the first half, like before manganese, this half, the most stable oxidation state will be the one in which all the s and d electrons are lost. And in later half, I have circled the most stable states. For iron and cobalt are plus 2 and plus 3. For nickel, it's just plus 2. For copper, it's plus 1 and plus 2, although plus 2 is more stable, we'll read. And zinc only shows one oxidation state, which is plus 2. Okay. And notice one thing, the only common oxidation state across all of them, except for scandium, is plus 2. Although scandium plus 2 is also same, it is very rare. So it's not mentioned here, but just a general point, I tell you, scandium plus 2 exists. Okay. So, like I wrote here, most stable in first half is the one which has all s and d electrons removed. But in later half, values are circled like those show the exceptions. And this is just a consequence of that. Wait, I made one mistake here. It has not been specified whether titanium has 3 more stable or 2 more stable. So just use a comma here because we are unsure. But one thing's for sure is that your titanium plus 4 is the most stable out of the 3 because all its s and d electrons are being lost in converting to plus 4 state. Okay. Now there's a possible question here from this line. The lower oxidation state stability increases left to right. Well, this is illustrated very well using this diagram. In the first half, we are being happy, we are going to plus 7 oxidation state, but it jumps down to the most stable state being lower as we move on and on. And in fact, after cobalt, none of them have the guts to show even plus 3 oxidation state. So just remember this order, that lower oxidation state stability, it increases as we go from left to right in a D block period. And this is practically the opposite of the inert pair effect. We know that for the inert pair effect, the higher elements, like I'm not talking about this left to right order, I'm talking about now top to bottom order. The higher elements, like basically, let's look at the table again. Higher elements like lanthanum, hafnium, tantalum, tungsten, they they are more comfortable with higher oxidation states. But in P block, the P block higher elements are more compatible with lower oxidation states. So this is practically the opposite of the inert pair effect. And this is an extra point of the NCERT. They can ask question on this. That see how molybdenum, tungsten, and chromium, they belong in the same group, like top to bottom. Okay, so molybdenum is more comfortable with a plus 6 oxidation state. Tungsten is even more comfortable, but chromium is not compatible with a plus 6 oxidation state, and hence chromium plus 6 is an oxidizing agent in acidic medium, and hence you read K2Cr2O7. Okay, we will cover this in the next lecture. And this is a point of distinction between the top to bottom. So far, we have only been studying left to right, except for the lanthanide contraction point. Okay, and basically when is low oxidation state shown when the complex has a ligand who has pi acceptor character. Just remember this line. We will learn more about this in coordination compounds. It has low oxidation, like low oxidation state is favorable when the complex has a ligand which has pi acceptor character. Well, let me just explain it to you briefly. This is the central metal atom. This is a ligand which donates electrons to this. You will not understand if you don't have an idea of coordination compounds. But if this ligand is willing to accept some electron density, some pi electron density in fact, from the central atom, then this becomes very strong. And this is what happens in cases of ligands like a carbonyl. Okay. So that was it about the oxidation states. We will learn more about oxidation states later. But first, let's move to electrode potential. What are the trends shown in the electrode potential? So first, let's learn about M2 plus 2M. What does this physically mean? It means that if something has a if it has tendency to move from the plus 2 oxidation state to the normal oxidation state, then if this process is spontaneous, then we call it that this electrode potential is positive. Okay. And this is the trend, like only for copper this is positive, which means only for copper this is spontaneous, which means that all these ions they prefer to stay in the plus 2 state, but copper prefers to stay in its metallic form. But why is that? The unique behavior of copper having a positive E naught accounts for its inability to liberate H2 from acids. Basically, if copper does not want to talk to this acid, it will not go in plus 2 state and make this and liberate H2, makes UCl2. It does not want to do that. Like this process is not spontaneous. And this is the inability of Cu to liberate H2 from acids and especially dilute acids. Only oxidizing acids like nitric and hot concentrated sulfuric acid react with Cu. Remember this as a general point. And why is this? Like why is it not able to do this? Why is it not able to liberate H2 from acids? And why does it want to stay in its metallic form? Let's learn about it using thermodynamics. In order to become from a solid metal atom to a hydrated 2 plus anion, cation. First, you have to go under the enthalpy of atomization. Like you have to go from solid to gas. Then you have to lose 2 electrons. And all of these energies, they are endothermic processes. They will take energy from you. But the hydration of it is a negative process. Exothermic process means it will release energy. In order for this process to take place, the product must be more stable, which means the negativity of the hydration energy must balance the sum of the atomization energy, the first ionization energy, and the second ionization energy. And in the case of copper, the hydration energy just fails to do that. Okay. And note that the E naught value for manganese, nickel, and zinc are more negative than expected, which means they have lesser tendency to go into their metallic forms than we calculated theoretically. Okay. Remember this as a general point. Now this is done. Oh, why is chromium 2 plus reducing and manganese 3 plus oxidizing? Basically, this has something to do with the geometry. Okay, chromium plus is not stable despite having a D5 configuration, and Cr3 plus is more stable. Now this is basically its reason using T2G. Like T2G, how do I explain it to you? D orbitals, there are 3 of them. T2G and EG. You know there are 5 types of d orbitals. 3 of them are in T2G and 2 of them are in EG. How do I remember this? Treat G as the greatest integer function. Greatest integer function of T. Treat T as 3 is 3. And G, greatest integer function of E. E is 2.718. It is going to be 2. Or you can just remember it's not that hard. T2G has 3 orbitals. And in T2G, basically, if 3 orbitals, they are half filled. So that is also going to impart extra stability. And instead of going completely D subshell half filled, it's just preferring to stay half filled in its T2G state. So chromium 2 plus is reducing. Remember this very well. Chromium 2 plus is reducing and it wants to go into Cr3 plus. It wants to get oxidized itself. Configuration changes from D4 to D3, latter having a half filled T2G level. We will learn more about this in coordination compounds. On the other hand, the change from Mn2 plus to Mn3 plus results in half-filled configuration. Like manganese does not have to deal with all this T2G stuff, and in fact manganese is more electronegative. So this results in half-filled D5 configuration, which has extra stability. Now, as we know, Cr2 plus got more stable by converting to Cr3 plus thanks to a T2G subshell, and the vanadium 2 plus cation gets stable in the same way. And we know there was an exception. I told you there was an exception to this where the cation wants to get half filled. So these were the exceptions that I was talking about. And credit to Mathhango for this PDF. Now let's talk about M3 plus to M2 plus. This is very easy. Basically, examination of the trends of basically M3 plus to M2 plus, they're going from third oxidation state to second oxidation state. So scandium does not want to go from this state to this state because Sc3 plus is very stable thanks to the removal of all the d electrons and all the s. We learned that if we remove all d and all s for the first half of the 3D subshell, it is going to be extra stable. So this reflects the stability of Sc3 plus, which has noble gas configuration. Now high value for zinc is due to removal of an electron, and we know that zinc 2 plus is very stable. So somehow if you make zinc 3 plus, it is going to come running towards the right side, because zinc 2 plus is the most stable oxidation state of zinc. You will never find zinc making Z and OS thrice. No, that is blasphemy. And high value for manganese shows that manganese 2 plus is stable, while manganese 3 plus is not stable. Basically, it all relates to that half-filled, full-filled things only. Okay. And as I told you, this V2 plus is also an exception. So comparatively low value for V is related to the stability of V2 plus, half-filled T2G11. Okay. Now let's learn a bit more about the oxidation states and ability of fluorine. Fluorine has the ability to stabilize high oxidation states. Why? They have asked this in a PIQ before. This is because that in ionic compounds, fluorine forms compounds with very high ionic, very high lattice energy. And in covalent compounds, it forms compounds with very high bond dissociation energy. Like covalent bond, high bond dissociation energy, it's hard to break. And it's basically same concept in ionic. It has a lattice and it will be hard to break. So fluorine can stabilize high oxidation states. And high oxidation states tend to be more covalent. Now, contrary to this, lower fluorides are generally unstable. Why? Well, we don't know, but it's not given here. But yeah. For example, like VX2 is unstable, COF is unstable, but MnO3F exists. Even though there is one fluoride here, three oxygens take charge and they stabilize the +7 state of manganese, and this compound exists. But unfortunately, COF does not exist because it is a lower fluoride. VX2 does not exist because it is a lower fluoride. Okay, and in fact, nickel, copper, and zinc cannot form trihalides at all. Like they cannot form ZnX3. We just talked about this. CuX3, NiX3. No, this is not possible. But CuX2 exists. Copper can make +2. But except for CuI2, CuI2 does not exist. It prefers to stay in the form of Cu2I2. Okay, take a look at this. This is a visual summary of all the facts we have studied. Now the next point. Many copper +1 state are unstable and are disproportionate to copper 0 and copper 2. Why is that? Well, because the delta hydration energy of copper 2 plus can balance the second ionization enthalpy of copper. We just studied here that in order for this entire process to occur, we want the hydration energy to be negative enough. And in copper plus, you only need one ionization energy, but in copper 2 plus, there is an extra competitor here, which is the second ionization enthalpy. But the increase in hydration energy from Cu plus to Cu2 plus, it more than well balances the extra competitor, and Cu2 plus hence is more stable than Cu plus in an aqueous medium. Okay. And this part, there were so many points here that I did not trust myself to write it down myself, so I just attached a screenshot. The ability of oxygen to stabilize the highest oxidation state is in the oxides, and this ability of oxygen surpasses even that of fluorine. The Now in the earlier half of the oxidation number. Also, don't mind the background noise because there are people celebrating a religious festival here, and that's fine. So let's continue. I hope my voice is more clear than their voice. Okay, so let's continue. So the highest oxidation state in the earlier half coincides with the group number. What does this mean? Scandium 3 plus is stable. So Sc2O3 is illustrated in the oxide. But in Mn2O7, we learned that +7 state is most stable. So Mn2O7 exists. And after the 7th group, no oxides of iron exist. But no oxides of iron except Fe2O3. Even I'm getting distracted by this music, that's why I'm stuttering so much. And ferrite exists, ferrite is this ion. They are formed in alkaline media, but even in alkaline media where it is imparted a little amount of stability, it still readily decomposes to Fe2O3 and O2. Now oxocations stabilize the D block elements. How? The fifth oxidation state is stabilized of vanadium is stabilized as this, the fourth as this. Titanium is already stabilized using 2 oxygens. Okay, and I told you ability of oxygen to stabilize high oxidation states exceeds that of fluorine. And the highest manganese fluoride is MnF4. Like fluorine could not convince manganese to let it make MnF7. But amazingly, oxygen was able to convince manganese. How come? This is because oxygen can form multiple bonds. As we know, the more the multiplicity of the bond, the more stable the bond will be. And this ability of oxygen explains its superiority over fluorine. Okay. Remember that Mn3O4 is a mixed oxide. It is basically existing at 2 moles of MnO plus 1 mole of MnO2. Okay, and look at the stable ones. These are also mixed oxides. They can ask you which of these are mixed oxides. So anything of the form M3O4 is a mixed oxide. Okay, especially for manganese, iron, and cobalt. Now, how would there's one NCERT question? How would you account for the increase in oxidizing power in this series? Well, this will reduce to this. This will reduce to this, and this will reduce to this. We know this is more stable than this, and this is more stable than this. So simply, it is easy to analyze. So thank you for attending this, and I'll try to do some noise cancellation. And we will continue this and end this in the next lecture. Thank you.